This video gives the working model and simulation of floating point adder. The floating point number representation has three parts: the sign, the exponent and mantissa. Depending on the precision required, whether it is a single precision or double precision, the number of bits assigned to each part differs. Here we are considering the single precision floating point representation, which is having one sign bit, 8 exponent bits and 23 mantissa bits. This module float add gives the floating point addition. The mantissa is 23 bits and the exponent is 8 bits as explained. The three steps required for floating point addition is: the first is the exponent equalization, the second is the mantissa shifting, and the third is the mantissa addition. The hidden bit should be properly considered to avoid the errors. So this module, this gives the exponent shifting equalization, and this gives the mantissa addition according to the shifted exponent with all the conditions. So now let us look into the test bench of the floating point adder. So I have included all the submodules required for the test bench here. That is float add.v is the top module, which is utilizing all these submodules. So now I have instantiated the module, float add module. Now I have given the inputs. Mode is equal to 0, that gives the addition initially. So AZ and BZ are the inputs called hidden bits. And since we have seen that there is one sign bit, 8 exponent bits and 23 mantissa bits, we have given all that into a single binary number. Let's say A and B are the inputs with 0 to 31, which is a 32-bit number. So I have divided each bit separately, like this is a sign bit of A and sign bit of B. This is the exponents of A and this is the exponent of B. This is the mantissa of A and this is the mantissa of B. This is how I have given the inputs, all in the binary form. And then we'll get the value change dump file. We'll monitor the outputs. And now let us simulate this floating point adder. So for that, we'll go into the same folder of this module. The simulation can be done using icaris Verilog. The command is as follows. Since I have given all the submodules in the test bench itself, I need not include them in the command over here. And -d 2001 is for the version. So for viewing the outputs, the command is bvpa.out. And here the outputs are all given as binary, since I have written the $monitor statement, everything in binary. This is to get a clear understanding of separate sign bits, separate exponent bits and separate mantissa bits. So A exponent and B exponent, A mantissa and B mantissa are the inputs. So CS is output sign bit and C exponent, C mantissa are the output exponent and mantissa bits. Now we can view the same in the waveform viewer using GTK wave. We can call the value change dump file that is generated from the test bench. So now we'll insert all the required inputs and outputs into the waveform viewer. So now the first set of inputs which I have given were 0.5 and 0.4. These are the hexadecimal equivalents of that values. So the output should be 0.9. Let's check it out. So the output is 3F and 6 sixes. So 3F and 6 sixes. So this is equivalent to 0.9. And then the next set of inputs I have given was 0.5 and 0.3, which should give up 0.8. that is 3F4 and 4C So this is 0.8. The next set of inputs that I have given were 1.2 and 1.5. That should give up 2.7. This gives 2.7. And then the last set of inputs I've given mode as 1, which is subtraction. That is 0.5 minus 0.2. No, 0.5 minus 0.3. That gives 0.2. So let us check this hexadecimal value. So 0.1 all lines is 0.2. So this is a simulation of a floating point adder. Thank you.